For example, segment anything is amazing. This is now it can segment anything to SAM2. Remember, we saw the demo of SAM2. Right? That was amazing. This is amazing. So the whole question is, and I would like to show you guys the demo of this is movie gen metadata. If you go here and look at the, sorry, let me just make sure that the recording has started. Wherever it is, I can't make that where it is. But it should have started. Since it takes time. Okay, is it recording? So, quick and easy way to see it. Yes, it has started. All right, guys. So if we go and ask, how is it that this is possible? That's the question. Right? We are going to read this paper in extensive detail. It's a 92-page paper, and I don't believe today may be the best way. But I would like to read the abstract and just the first couple of paragraphs. We present MovieGen, a cast of foundational models that generates high quality 1080p. Now, that word is important. You notice that there are a few movie video generators, but they all generate low-res videos. When you talk 1080p, right, you're talking of very high resolution, right? It's high def, and obviously, I would imagine that 4K would be the next step with different aspect ratios and synchronized audio. We also show additional capabilities such as precise instruction-based video editing. Pay attention to the word instruction-based video editing and generation. What we will do is today, literally, the first paper in this front was visual instruction tuning. We'll start with that. Based on a user's image, our models set a new state-of-the-art on multiple tasks, test to video, blah, blah, blah. So now the rest of it goes into the protocols, right? But this statement is good. We show multiple technical innovations and simplifications on the architecture. Actually, the important thing is simplifications. It's not that they created a bizarrely complicated architecture to do it. Latent spaces, training objectives and recipes, data curation, evaluation protocol, parallelization techniques, and inference optimizations that allow us to reap the benefit of scaling pre-trained data, model size, etc., etc. Right? All the videos are here, the blog is here, and so forth. And obviously, it would be nice if there was also a GitHub page, but it isn't yet. I'll read the first paragraph. Imagine a blue emu swimming through the ocean. What's a emu? I don't know.
It's like a smaller version of ostrich.
Ostrich.
Okay.
Yeah, swimming through the ocean. Humans have the astonishing ability to imagine such a fictional scene in great detail. Human imagination requires the ability to compose and predict various facets of the world. Simply imagining a scene requires composing different concepts. This line is important. While predicting realistic properties about motion, scene, physics, geometry, audio, etc. Equipping AI systems with such generative, compositional, and predictive capabilities is a core scientific challenge with broad applications. And now comes the statement, while large language models aim to learn such capabilities with a text output space. LLMs, what is the output? Tokens, right? Text tokens, output space. In this paper, we focus on media, image, video, audio as the output space. Okay. We present MovieGen, a cast of media generation foundation models. Okay. So they're going to present a few foundational models. Oh, the font, yeah. Let me increase the font. Okay. MovieGen models can natively generate high fidelity images, video and audio, while also possessing the abilities to edit and personalize the video. We find that scaling that, so next sentence, pay attention to. We find this that scaling the training data, compute and model parameters of a simple transformer-based model trained with flow matching yields high-quality generative models for video or audio. So let's pay attention. You know that transformers follow all neural networks follow the neural scaling laws. What do the neural scaling laws say? That you get better abilities, better performance if you carefully and optimally scale up parameters, compute, and data. Right? You have to sort of in a coordinated way lift it, and you have the concept of chinchilla optimal and so on and so forth. We have covered those things, have we? Yeah, right. We have covered this. With flow matching. Flow matching is something I usually cover in Intro to AI. How many of you were there in my flow matching session? Last time, we overspilled it, like we didn't cover it in the regular, but in a supplemental session. Right? So the flow matching is a class of models. Anyway, many of you are again taking that course, then we will be covering flow matching. It's a very powerful approach. So they're hybridizing two things, right? So they're bringing these two things together to yield high quality. Our models are pre-trained on internet scale image, video, and audio data. So internet scale means, hint, it's Facebook, right? It's pretty obvious. They have access to a lot from the internet and vast repositories of their own data. Our largest foundation, a text-to-video generation, movie gen video, consists of 30B parameters, while our largest foundational video-to-audio generation model, movie gen audio, consists of 13 billion parameters. Guys, I want you to notice today, would you consider 30 billion and 13 billion massive models? No, you would not. But actually in the vision world, these are big models. If you remember, last time when we did blip 2, those were much smaller models, isn't it? If you remember, we covered blip 2. What did we do in blip 2? We took a very good image encoder, clip encoder. Pick your large language model, whatever you pick, LLaMA or something. And then in between, we sandwiched a Q-former. The Q-former was not even a billion. It was like 100 million or so parameters, tiny. And it produced results. So in the world of vision, computer vision, models tend to be 1 order of magnitude or 2 orders of magnitude smaller so far. So within that space, a 30 billion parameter model is actually a significantly large model. Right? It's a big model. And 13 million. So we further post-train the movie gen video model to obtain personalized movie gen videos that can generate personalized videos conditioned on a person's face. We saw that, right? The picture of that lady. We saw a whole video in her pumpkin patch and so forth, I suppose. Finally, we show a novel post-training process to produce movie gen edit that can precisely edit videos. Did we see that? The runner becoming a dinosaur and so forth. Finally, we show a novel post-training procedure to produce that can, in conjunction, these models can be used to create realistic personalized SD videos of up to 16 seconds at 16 frames per second and 48 kilohertz audio. 48 kilohertz audio is standard. 16 frames per second is normal, right, for movies. Now, the video length at this moment, so there are two limitations that you see. First is that it can do only HD videos, and the second limitation is length, 16 seconds, right? So that is that. So now, while this is good, and we are going to cover it next time, what I will do, and observe something very interesting. I want you to just absorb this architecture because we will come to this. See, what do you see? You see transformers there, of course, expected. You see the so-called temporal autoencoder model. Whenever we do, if you remember your last time, in the last few weeks we have been talking, we have been seeing these autoencoders pop up everywhere. You'll see it very much in progress. Whenever you see Gaussian noise, what does the Gaussian noise signify? It often is the latent that you inject into it. for variety, right? So to affect the generation aspect of it is the Z, right? So think of, for example, if you were to think of the GAN, what does the generator take as input? Noise, Gaussian noise, right? So this is it, is happening. So this architecture, let's not dwell too much into it because we're going to do it in great detail. But I want to start with something simpler that lays the groundwork for what we are going to do. Today's topic was actually not this, but I wanted to show this to you because we will incorporate it into the course. Today's topic is LLaVA. How many of you have heard of the LLaVA models?
Only the term.
Only the term. Okay. So today is certainly the day we are going to learn about LLaVA. Let's go and do that. By the way, as I'm reading this paper, you might have a sneaky feeling, nobody has heard of these papers. Are they really significant? CLIP. You think the CLIP was a significant paper? Anyone would like to venture a guess? Let's find that out and see the number of citations that it went through. Likewise, CLIP 2, archive. Let's look at blip 2 and obviously blip archive. See, this thing can count only till 9999. Number of citations. So CLIP, I suppose this answers the question why I'm covering it. See, guys, we are at the frontier. There are no good textbooks at this moment on the things that we are discussing in this course. We have to necessarily read from the research papers. Textbooks will come, but you realize what does it signify when the textbooks come? It's already commoditized, and most likely it's already being outsourced out of Silicon Valley. Yeah, isn't it? So our opportunity is right here. We have to read from the textbooks, but rest assured, I'm covering only the most important papers. Likewise, this is blip 2. Look at that, 2,590 papers, right? What are these citations? These are not some hyperlinks from some web article. These are other research papers that are quoting this paper, right? So 2,600 research papers within a year and a half have come out that refer to these papers as found, like these papers are of such foundational value. This CLIP came out a little while ago, 2021. Right? You can say 3 years have gone by, but look at this, right? So this is the closest thing you can come to textbook at this moment. That's why I'm taking you through these research papers. There is no, anything else is actually will not be a very good alternative. Likewise for blip, if you look at the number of citations, you will find that it is also in the 2000s, 1,000 or 2,000 level. Most people would love it if they get so much as 20, 40 citations to their paper, right? We are talking here of hundreds, thousands. So these are important. Today, the paper that we are going to do is LLaVA. Which represents quite an interesting milestone. One of the things that has been happening, look at the date of this paper. It was submitted on April 17, 2023. What do you think happened around that time? ChatGPT came out, right? Just before that, November, it had come out. And you can already see people asking this question. Can we use instruction tuning to create better visual models, like multimodal models? Are we together? And that is the significance of this paper. If you go back and look up to CLIP, blip, and blip series, you don't see it exploiting prompting itself, isn't it, guys? You don't see it using prompting or instruction tuning and so forth as much. There is fine tuning for sure, but not instruction tuning. So the importance of this paper is, amongst other things, it was one of the early works that seriously explored bringing data generation from the LLMs to create training data for multimodal languages, the multimodal models, right? So it's a very interesting paper. And as I read it, please do pay attention, because this paper you should be able to remember very well. So look at this. This has garnered 2,000 citations, right? When did it come out? Just a year or so ago, right? A blip also, 2,800 papers. So these are very important papers. And today we are going to do one more paper which just came out, as in came out when? Uh, 3D. We are going to do, so these two papers we are going to do. The rest of the time we'll build something practical. Today our day was somewhat abbreviated because of this. This paper came out in 26, 1 week ago, right? So I'll cover these two things because they are both important papers. And of course, time permitting, I'll also do movie gen today, or I'll do it, actually, I'll let you absorb it and we'll do it the next time. We'll do that, and we'll also do SAM and SAM series next time. But in the meanwhile, we'll do something practical. So let me insert. By the way, does anybody know if there is a way for me to invert the colors in a PDF, like change the background to black and the text to white in a PDF? Anybody knows of a technique to do that, or an easy way to do that? Edit the PDF into it, maybe, yeah. So I need to explore that. So LLaVA 3D, let me go to the desktop. Let's see if I have LLaVA. Oh, I don't have the LLaVA paper. It's time to download it. LLaVA. Just oh, it might have been in paper reading. LLaVA. LLaVA is there. Sorry, I was looking in the wrong place. Just so your work today, guys, is to do a lab on LLaVA, right? It is really very powerful, especially its application. One of the people from our own class, a previous batchmate of yours, is extensively using LLaVA for annotation of medical images, right? So it is gone way beyond just being research curiosity. It has been fairly extensively used. So let's pay attention to this. Let's read what this paper has to say. It is actually, compared to ClipBlip, in some sense, the architecture is simpler. The idea is innovative. First of all, they have a very good GitHub. I encourage you to visit the GitHub. You'll see the code, you'll see everything there. And let's read this. Instruction tuning large language models using machine-generated instruction following data has been shown to improve zero-shot capabilities on new tasks. But the idea is less explored in the multimodal field. What do you mean by instruction tuning large language models? Remember, that was the work of InstructGPT, that you don't train it with some, the old idea was that you would give it a text, right? You would say the cow jumped over the, then you would wait and see, let it produce more. But to instruct tuning is to prefix it with the instruction saying, give answer in yes or no. Right? Is a cow a plant? Right? Then the answer that you expect is a no. Right? So that is instruct tuning a machine. So large language models have gone through a lot of instruct tuning. In fact, the reason they respond so well, amongst other things, like for example, if you look at the Instruct GPT paper that led to the rise of, did I cover the Instruct GPT paper? The fact that you have pre-training, supervised fine-tuning, human. I have not done that. That's a very important paper, and I will do it right today itself. But at this moment, take it from me that there is a process to train models, LLMs, and one of the discoveries was that if you give instruction before the text that you wanted to respond to, and fine-tune the machine to respond to those instructions, to respect those instructions, you get very good results. In fact, that was one of the big breakthroughs in this field that made the transformers very, very useful. Right? And you can only do it with sufficiently large models. So which brings us to the whole concept of neural scaling laws. We have covered the neural scaling laws.
Yeah.
So we did that. So what they're saying is instruction tuning you can do for large language models, but not much this direction has not been explored for multimodal field. Because in multimodal, what would you say? You would have to give things like, instruction would be something like, is there a cow in this picture? And then you would give it a picture. And then you would have the machine answer something, let's say here, yes, or what is the color of the cow, or something like that. So such data sets are hard to get. They don't exist. Because they don't exist, you have a chicken and egg situation. You can't do a multimodal fine-tuning of transformers, isn't it, of models? Because you say the idea looks very good. I can give an instruction, but instead of giving it a text, I can give it an image. And then I know the answer, and I can do a loss function on the answer to make sure that the answer that you get is the answer that you hope for. Am I making sense, guys? Yes. Am I making sense? Right. So to make it very simple, I could do this instruction, image, and here is the answer that I expect. If I pass this, and whatever answer it gets, this is your y, whatever it gets, I can create a loss function between y and y hat, right? And therefore train the machine to follow the instruction. For text, I can do it, but for images, the main problem is, where is the data set? We don't have the data set, right? So that is the main problem that this paper raises. And this is, remember, April 2023, ancient history, right? So we present the first attempt to use language model only, language only GPT-4 to generate multimodal language image instruction following data. So they are saying that, see, this problem, if I want to solve the one that I'm showing you on the right, what do I need? I need lots of training data, right? Because to train a model takes data. So first we need to create the data. So the creation, so that's the first part of it. This is what we present the first attempt to use GPT-4 to create instruction following data. By instruction, then the second part comes. By instruction, and that's the second part of the conclusion. Why would you want to create such a data? You would want to then train a model, LLaVA, large language and vision assistant, they call it, an end-to-end trained large multilingual model that connects a vision encoder and a LLM to general purpose visual language understanding. So you could already have sort of anticipated the pieces. By now we are familiar with the encoders, right? Clip, VIT, clip, etc. So we do need, given an image, some part is no-brainer. We will get some latent representation of the image. This is true. If you are going to output the result from some text image, like answer to this question, y hat, which is textual, then you certainly need a LLM these days because they are the state of the art. Now the only question is, what is in between? So you will realize that these two pieces of the puzzle by now, if you have been, as you go through this workshop, that part is obvious to you, isn't it? And so whatever magic they did has to be the part, what is happening here? That is what this paper is about. Right? So two parts of the paper is, first they will create the data and then they'll train the machine. It turns out that what they do in those two question marks is very, very simple. Right? So think about it this way. LLM takes certain inputs.
That's only text.
Right. And all you need to do is somehow align this and your instruction. So remember, you're not just giving that. You're also giving instruction, which is text, some text. The text, of course, you can easily convert it into a hidden state for text encoding, text encoder, right? So now we have three pieces of the puzzle already in place. Oops, what happened? Give me a moment. This thing is jumping around. Yeah. Just today is the day for all sorts of. Okay. I have lost the ability to engage with this for some reason. Let me close this and start it again. I apologize for the distraction. So we need an image encoder, obviously, to create latents from the image latents. Go ahead, Mandeep.
Why can't we just use like blip or blip to get the data?
No, they're saying there's a simpler way.
Even that.
Yeah, you could have done that, but what they are saying is that let us see if we can use a large language model to generate data instead. And you'll see why they did that. When you, oh, now I got my interactivity back. Okay, so now look at the puzzles. You know that you're going to give it text as input. You're going to give it image as input. That's a multimodal nature. You will need an encoder for this, and you would need an encoder for this. Text encoder, just think bird class, something, right? Encoder. Bird, for example, bird-like. Bird-like. Text encoder will produce a hidden state of the text. Image encoder, right? A semantically meaningful, for example, you could use clip. You can use clip, blip, whatever you want, or a VIT, clip, blip, whatever. Will produce a hidden state for the image. But now these two hidden states may belong to different dimensions. So you'll need something to align the dimensions, right? Yeah. You will need some sort of a projection matrix. You will need, in the very minimum, a projection matrix. And when there's a projection matrix, there may be also a great temptation to bring in some feed-forward network, do some deformations. You realize that, right? Why not? While you're at it, why not? And then finally, you know that there will be an LLM. So that, having, from everything that you have learned, and even before you read the paper, would you not infer an architecture, something like this? Right? Now, let's see what they have done. Oh, look at this. Let's pay attention to this picture. What are they doing? XV is your image. It is getting, vision encoder is creating a hidden state, H, for the vision. I used I, they're using the vision. Now, why are we having a projection matrix here? To align it to the same dimension as the HQ. They're not bringing in any feed-forward network, actually. So I thought there would be, but they are. And then all you have to do is, you are ready to feed it into an LLM, which you can fine-tune. Does that make sense, guys? This language model is the LLM. And so, from everything that you have learned, do you notice that now, hopefully, you guys are capable of just thinking when people describe, we did this. I hope you are gradually developing the ability to infer, at least roughly, what is it that they would be doing. Are you able to? Isn't it? Right? You're able to, and that's what this architecture is about. So let's read it a bit more carefully. Now, well, that's not the hard part. The hard part is, how do you create the data? Right? And the way they create the data is a pretty clever argument they use. So we'll read through this. Okay, let's read the rest of the abstract. By the way, are you having fun with this? Yeah. It's lovely, right? So now it says, to facilitate further research on vision instruction following, we construct two eval benchmarks. So along the way, they also create a benchmark. Our experiments show that LLaVA demonstrates impressive multimodal chat capabilities. Look at this. Instruction tuning a transformer produce you a chatbot. Instruction tuning an LLM, right? In this particular method, essentially gives you the ability to talk to your document. We'll see whether that's true or not in a moment. Chatable, sometimes exhibiting the behaviors of multimodal GPT-4 on unseen image instructions. Right? So obviously it generalizes to, if it doesn't generalize, then it has just memorized, which will be useless. Of course, it has to generalize it, but it yields a 85.1% relative score compared with GPT-4 on a synthetic multimodal instruction following data. So basically, they're saying they're doing very well. And as you will see, the state of the art that they've achieved is very good. So let's look at the results. Right? Before we look at the method, let's look at the results. Let's look at this image. So this is a pretty challenging image, right? Just a challenging examples from the LLaVA benchmark, which by the way, they created as part of this paper. So they create three things. They create a data set, they create a model, LLaVA model, and they create a benchmark, LLaVA bench, which now is pretty accepted. They're saying the source is Ichiran ramen. How many of you have eaten this? I have no idea what this is. Yeah, I like ramen, but this one I don't know. But okay, let's read it. Annotation. A close-up photo of a meal at Ichiran. Oh, Ichiran is a restaurant. The cashew ramen bowl with a spoon is placed in the center. The ramen is seasoned with chili, etc., etc. On top of that, yeah. And like, how many of you would be impressed at this detailed understanding of this image? Read it. Chopsticks are placed to the right of the bowl. Actually, you would have missed it, isn't it? But sure enough, those chopsticks are hiding in the packet. And still in the paper wrapper, not yet open. The ramen is also served with nori on the left. Wow. On top, from left to right, the following sides are served: a bowl of orange spice, possibly garlic sauce, a plate of smoke-flavored stew pork with chopped scallion, and a cup of matcha tea. Let's look at the fridge here. An open fridge filled with a variety of food items. In the left, a part of the compartment towards the front, there is a plastic bowl of blood. So it itemizes all of that. Page 9. Table 6, it says, challenging examples from that. We provide extremely detailed annotation for each image. For an accurate way, some questions require the model to extract data from high-resolution image and to have a broad knowledge, right? So first, focusing only on the results. Guys, it suffices to say that if you look at the LLaVA plus GPT results with our experiment runs, you realize that they are significantly better than the table above, comparing it to GPT 3.5, Llama adapter, this and that. In average, you're getting a 92.53% score, accuracy score. So imagine a machine that can look at an image at 92.53%, it gives you the right answers. That, by the way, is about the level of a human being.
Interestingly, even without GPT complementing it, it is still almost on par.
Yes, it's doing very, very well. Yeah, and they do all sorts of studies. Let's look at an example. These things are much more real when you see real examples, which I trust they have it in the paper. Look at this. This is one of the internet memes. At the top, it says, sometimes I just look at pictures of the Earth from space and marvel at how beautiful it is. It all is. And then there is this cookie tray with sort of a mock-up of the map. Let's see what GPT-4 says. GPT-4, the same question is given. So first of all, it's given to some lesser models. Like, let's say it's given to Blip2. Now, I trust last time you were very impressed with Blip2, right? But now this time it says, sometimes I just look at the picture of the Earth from space and marvel how beautiful it is. So it just more or less regurgitated it. Flamingo. Now you can ask for your money back for last session. Right? I'm kidding. So the Flamingo says, can you explain this? It's a piece of chicken nugget on the International Space Station. It hallucinated. What did GPT-4 say? This meme is a joke that combines two unrelated things, pictures of the Earth from space and chicken nugget. The text of the meme suggests that an image below is a beautiful picture of the Earth from space. However, the image is actually of chicken nugget arranged to vaguely resemble uh, a map of the world. The humor in this meme comes from the unexpected juxtaposition of the text and image. The text sets up an expectation of majestic image of the Earth, but the image is actually something mundane and silly. Right? Now, reasonable, but now let's see what LLaVA has to say. The meme in the image is a creative and humorous take on food. With a focus on chicken nuggets as the center of the universe, the meme begins with the phrase, sometimes I just blah. So it reads out the whole phrase. The main image features a tray of cooked chicken nuggets with the chicken pieces positioned to resemble the continents and islands in the world. The meme playfully suggests blah, blah, blah. How many of you feel that this is pretty impressive, right? Then, with some pictures, but here's the thing that will blow your eye. You hand draw a picture. Now pay attention, this is April 2023, remember ancient history. April 2023, you hand draw this picture. And then you say, turn this mock-up into an interactive website using HTML and JavaScript, replace the joke with a real joke. So you give it two things, right? And the question is, and this is your multimodal models, power of multimodal. And what comes out? Right?
The image converted to text on HTML code.
Yes. And here is the thing. Here's how the page looks. My joke website. Welcome to my joke website. Push the button to reveal the punchline. So you push me. And then when you push me, it says, why was the math book sad? Because it had too many problems. Right? Right? But see, do you realize the potential of it, guys? By the way, a lot of the product managers, they create mock-ups and then they ask the engineers, when will it get done? They say, well, let me think. Okay, this will take 6 months, that will take 6 months, that will take 6 months. So 18 months later, you'll get it, right? So now this is becoming, as you know, this was 1 year ago, more than a year and a half ago. Right? So if your colleagues and your friends haven't woken up to the fact that software engineering, as we know it, is dead, is going through a transformation. Any software engineering will do hereafter is with AI. We are steering it. Right? A lot has happened since then. Now, the situation is even more like SQL generation gone. A lot of this React code and all of these, the latest models, multimodal models that are there, they have like taken over. In fact, it's almost foolish to create things from scratch now. You want to make rapid progress. You want these machines to generate the first draft and then you make progress from there. That is happening. So that's a fun topic. Here's a hard question. You look at this image and say, what are the meals that I can cook with these? And it says, isn't that the question you ask when you go hungry home and look at your fridge? Yeah, with the variety of food items stored in the refrigerator, you can prepare several meals. For example, you can create a fruit salad using a strawberry blowing. Additionally, you can make a delicious smoothie. Guys, I just leave you.
Really terrifying.
So the same instruction give to what is there in the refrigerator?
Yeah.
Pass into
Understands
that.
exactly.
Cook also happened, right?
Yeah.
What? You wanted to cook also?
Yeah.
No. So here's the thing. Guys, in one of the courses, which is the AI agent, guys, in a course that is AI agents. Yeah. By the way, I just finished a course called AI agents, multi-agent. So there you use tools. So the next step is the natural evolution of this is agents. So there was a real experiment we wanted to do, but I couldn't because we ran out of the funds to get a robot. But one of the exercises that in that course we didn't do in the tooling was quite literally this, that you ask the agent a question, the agent comes up with an answer, right? and then realizes, no, like there will be a doorbell in the back. Listens to that, says, huh, I think somebody is at the door. Goes to the front with a glass of water to welcome the person. That was literally the, and along the way goes to the kitchen, says, let me take a welcoming glass of water. And then goes to the door. Right? And then we rig it. Like the idea was to rig it to say that because of the facial recognition, the multimodal facial recognition, it would say that, oh, this is Kanwa. Kanwa likes water when he comes. Right? So let me take a glass of water. We wanted to do that, the whole setup. Unfortunately, the enrollment was a bit low. We couldn't do that. But next time you do the AI agents class, come to that. You'll build all of these things. So to your question, can it also go cook? Yes, that day is coming. And
the meta glasses that they have revealed now, people have actually made like, let's say it is, I'm looking at you wearing the glasses. It will go scrape the web, find out your distance and display in like a web page all the information that you can find.
Absolutely. Augmented reality. Augmented reality is the future. See, guys, first came virtual reality. But trouble with virtual reality is that you either look at reality or the virtual reality, right, in the goggles. So, and then the older generation begins to feel giddy. Like they feel dizzy wearing those glasses. So now the big push seems to be augmented reality. That you're looking at reality and the additional information is augmenting. And when you attach it with agentic reasoning, it is acting upon it, doing things with it. So I would, by the way, not as this, but if you find all of this interesting, come to the agent scopes. You will see something interesting. You will see, for example, an illustration with it. The agent, how many of you would like to see this? See, you know that you make a LLM write some code. It will have bugs. Can have bugs. It may not be right. For example, you don't know if you give it a complicated problem, it can be wrong. So here's something we do. This is a real lab, which we demoed solution. There's something called open function calling. You give LLM, which understands the APIs of a lot of open source projects. In this particular case, PyTorch and Hugging Face and so forth. You give it a problem that you have to do this, a multimodal problem. You have to understand the text, and after that, some part of it, you have to convert it into sound, whatever it is. And it had to go and do it by reading the Hugging Face in PyTorch. It did it. The code was wrong. It had a subtle bug. And why was the code wrong? Because in engineering, documentation and code never stays aligned. So guess what happened? That open source project had changed the API, but had not changed the documentation. So based on the documentation, the LLM wrote some code. It didn't work. Another agent says, let us sit and think why it didn't. Then another agent said, could it be that the documentation is old? Right. So now what things we can try? And so all these agents, they interact together and they try variations of the code till it works. Isn't that what you would do if you don't have documentation? Right? You would try different variations and things. They did that. They wrote the code. Then they asked, collectively, those agents asked, how do we know that this is right? They say, okay, maybe we need to write a unit test to verify this. And they sat and wrote a unit test. And then they invoked the code. They saw the response. They all agreed that, I think we all agree that the response is correct. Right? This is what I made people do in the class. Right? Well, a smaller version of this, some part of it we left it to them, right? Can you imagine after this applying for a traditional software engineering job without AI awareness? AI is a tool. It's like going and saying, I'm going to do accounting, but by the way, don't make me use computers and spreadsheets. Right? You are in a new age now. So, okay, guys, here it is. I would like to do the fruit salad. Show me the recipe. It produces the recipe. Look at this. What are the things I should be cautious about when I visit here? So stare at this picture a little bit before you answer this, or you look at this. Just what are the things I should be cautious of? What would you say? Water, right?
No railing.
No railings. What else? Now let's see what the machine said. When visiting this peaceful location with a pier extending over a serene lake surrounded by mountains, there are several things to be cautious of. First, pay attention to the weather conditions, as sudden changes in weather, especially strong winds or storm, can cause the water to become rough and pose risk to the stability of the pier. Piers of, right? And that is if it's a floating pier. Second, be mindful of the structural integrity of the pier. Avoid overloading it with too many people or excessive weight, as this would potentially damage the pier, cause it to collapse. Additionally, be aware of the surrounding wildlife and respect their spaces. In case there are some crocodiles there, I suppose. Do not harm or disturb them in any way. Finally, if you decide to go fishing, ensure that you adhere to any local fishing. Does it sound like your mom giving you instructions before you go on a picnic?
Yeah.
Right. So
That's interesting. While there is good things here,
yeah,
I'm not completely impressed by the cost.
yeah,
I would say it's good. It's computer generating this is impressive.
yeah.
Like I would have expected some of the ravens, and I don't think there will be a storm in that. It's a small lake.
Yeah. Try it out today with the latest version of, remember this was first version of LLaVA. LLaVA 1.5 onwards, much better, much better. Compose an engaging travel blog about my trip to this place, right? Highlighting the beautiful scenery, blah. So guys, while you're at it, so I'm told that half the travel blogs on the internet are imagined. So here you go, right? In case you want to make your friends envious that you had such a good time while they were busy taking weeds out of their backyard. Right? Here it is. Here's your traveling blog. Traveling to this picturesque location, blah, blah, blah. One of the highlights of my trip was undoubtedly the fishing experience and whatnot. Oh, this is a bit funny. What's the ending of this movie? Right. Well, suggest, obviously it says there was a sense of romance and nostalgia. This part I found really funny. Do you know who drew this painting? This is, of course, yeah. So it says the painting depicts a dog in a humorous situation where it appears, blah, blah, blah. So obviously nobody drew it. It's like a spoof, right? Replacing a human with a dog dressed in a woman's clothing and so forth. What is the name of the man in this picture? It gets it right. Here's the better part. What is the name of the man in the photo? Right. And the name of the man in the photo is still Elon Musk. And so forth. So guys, I won't go more into it, but I'll give you a real problem. Now the question is, how does this happen? Are you interested in knowing how this is done? See, given an image, if you have to create instructions, you can create some bland instructions like this. Describe the image concisely, etc., and expect that. But the trouble is, those are not very good data. You need better quality if you want to really create a high-powered model. And I'm sure they must have tried this and realized, doesn't go anywhere. Right? You need better quality data, training data, because a model is only as good as the training data it has learned from. So what you do is, and what they do, and now I'll tell you what they did, besides that, to create the data, they did something quite lovely, actually. And I want you to spend the whole day, guys, okay, by the way, look at this. What is unusual about this image?
Mobile lining.
Mobile lining and
The unusual aspect of this image is a man ironing clothes on the back of a minivan. This is not a typical place, blah, 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 right? Oh, by the way, in India, you see, in my time, when I was young, in the train, you would have this person who would have this little vendor, who would have this little tray filled with some things like peanuts or something like that. And he would be holding onto the train, one of the window bars in the train while the train was moving. And with the other hand, he would be selling you the little packets of peanut and taking money from you. Pretty dangerous, isn't it? But I don't know, somehow this picture reminded me of that. Right? So, very unusual picture. So, So now the question is, how did they do it? How did they do that? This is it. Actually, when you see how they did it, is simplicity itself. See, look at this picture. From this picture, you can use a segmentation model to create bounding box around things, isn't it? We have AI to do that. Beaten to death, go use YOLO, whatever it is. You can do that. So, second part is the person, black back, all the things that you see in the image. Somebody has written a caption to this image. Now, I'll take those images for which there is a caption. So here's the thing. Thanks to blip2, we have caption data. We have an ability to caption the images. Are we together, guys? You can use blip2 to generate all these lovely captions. They go do it, or whatever it is. Or humans go and generate captions, or whatever. By whatever means, go generate good captions. Then review it, make sure all the captions are correct. But then augment it also with the bounding boxes of the people. Give both of it to the LLM. So notice, don't give the LLM the picture. LLM doesn't understand picture.
Yeah.
It only understands text.
Yeah.
So you give it these two pieces of text, the caption and the bounding box text, right? The person is at this. Do we know what a bounding box is, guys? See, bounding box is the concept that, suppose I have a duck in a picture, right? Then what you do is wrap it up in a box, the smallest box you can wrap it up. And then you can, you realize that you need the X, Y, X prime, Y prime. These two. Does that make sense? If you had these two locations, you can draw the, the coordinates of it, right? Or I don't know, maybe I have interchanged this, or it could be X. Sorry. I keep forgetting this location all the time. It could be X, Y, X prime, Y prime. I don't know, doesn't matter. Either of the two pairs will completely describe your box. And then if I put the label duck, that's it. And I can give the 4 locations. That's why you see 4 numbers. Why? X, Y, X prime, Y prime. Isn't it? So those are called bounding boxes. But here is what you do. You tell the LLM, you give an LLM, which LLM? GPT. You tell GPT-4, which is a big model, you give it an instruction. You say, it doesn't have access to the picture. It has access to just these 2 texts. You give it an instruction. Please now, based on the context and the location, create some interesting question answers for me. It's a data generation question you're asking. Do you see that? Right? We are saying create some interesting question answers for me. Right? I'm just sort of paraphrasing it. You can go and look into the paper, what exactly they wrote as a prompt. But basically, that's what you're prompting it to do. So what will the machine come back with? It will say, okay, you want me to do that? Here's one. What type of vehicle is featured in the image? And the answer is, the image features a black sport SUV, right? So you realize, guys, that this is not just like describe the image, a generic question. It's very specific to this image, the question answer, right? And so if you use the question and the image, now what happens? So you can go create a lot of data like this. You can also say, give a detailed description. It can give a detailed description. So it will elaborate on the previous discussion. It can also go and produce complex reasoning. Say, give me a question answer that's a little bit harder than just looking it up. So it can say, what challenges do these people face? In this image, the group of people is standing outside a black SUV in a parking lot surrounded by a variety of luggage, including suitcases, etc. They face the challenge of fitting all their luggage into the black SUV. There are multiple rubber. Isn't that the challenge all of you people face when you're going on vacation? Right? So, well, there we go. Now, what do I do with all of this image? See, what have I gotten? Let's start thinking about it. By the way, let me reiterate the point. When you give it to GPT-4, are you giving it the image? No, you're not giving it the image. You're only giving it context type 1 and context type 2, means caption and the bounding box. That's all you're doing. Now, think of So this is step one of the journey. Using this, you can create training data across gazillions of these images. Do we agree? And so one part of the problem that they mentioned in the introduction is solved, abstract is solved. There was a paucity of data. There was a lack of data, multimodal instruction data. Have you just created a lot of multimodal instruction data? You have. And so what is the next part? The next part is almost a no-brainer. After that, what do? You go to the image. You go to the image, take the image, and its associated caption and natural trait. No. Now, what you do is you start feeding this in here. Now you realize, so you throw your GPT-4 away. You go and take an open source model, simple open source model. In this paper, they took Vicuna. In those days, Vicuna was the as powerful open source LLM as you could. Those are smaller models. So today you would take Llama 3, 3.2, right, or something like that. You take that. Those are much smaller models, right? And then, so let me put the word Vicuna here, or Llama. And now you do this. You take your model, pass it through the visual encoder, pass it through the projection. Does that make sense? You get a latent state. Now the question is, what is your question? What is the text that you give? Language instruction. Language instruction is derived from your, literally, you just created it, right? Through GPT-4, right? And then you do this. So guys, do you see something interesting happening? You're using a bigger model, which is successful in a different domain, pure text domain, to train a smaller new model in a multimodal domain, right? And you see the emergence of a practice which has become very common. You generate data from an LLM to train another LLM. It's become very prevalent these days. It's very common. So we do that. This makes sense. And the rest is, of course, making sense, I hope. Right? Yeah.
So again, the text is it again in the training? Are they going to validate that?
Yeah. So what happens is that, see, you know the question and the answer,
Yeah.
right? And so all you do, so guys, what happens? You give it an image, you give it the question that you have in your data set. This machine will produce an answer. What do you need to do? This is your why, right? But you already know the answer, which is the
That's why I have.
why,
That's
yeah,
the-
why hat, right? Sorry, you know the why that the GPT-4 produced, and whatever this machine produces is your y hat. You can therefore produce a loss function on top of it, and you can minimize that loss. And you can go on training this machine over gazillions of these instructional data, multimodal data now. Why is it multimodal? Because you're passing in an image and a text. You're expecting a text in response, which you have a reference text to compare to, isn't it? And so you can do a multimodal training of this model.
Can you call this agentic way of training?
No. This is not it. This is just multimodal, straightforward multimodal. Right? Yeah.
The bounding, does it happen in the language, the image boundings, right?
Yeah, no, because you use YOLO or something like that. Some other models.
Which
Yeah.
is prior to that in the visual.
Yeah, prior to that.
Okay.
Prior to that. So one of the questions that I think somewhere they must have answered in the paper, but I forget, how in the world did they get the caption?
Yeah.
Quite often captions are human generated, but of limited number. Now there are many data sets with high quality captions. They exist. How were they generated? I would guess that part of them was human, part of them was using blip2 or something to clean up and generate it. That's what my guess is. Now, when it comes to bounding box, how do you do it? Oh, that segmentation is very mature. YOLO, etc. will do a fine job.
This is the question.
CNN would do it, but these days you do it using transformers, VITs, etc. But
That's
yeah,
fine.
very mature. Yeah.
So the question is, like, I know image was, the question is contained only the question part or even the answer also?
No. Answer is so think of this way.
Answer is my way.
Yeah, exactly. Answer is your y. This is your y. This is your x q, and this is your x v. When you're training the multimodal.
Or in the training time.
Yeah, yeah, that's right. In the training time. So what happens is xv will go into the image encoder. encoder. Q will go into the text encoder. This also is no-brainer. This will produce a HV. This will produce a HQ, isn't it? But the problem is their dimensions won't match. So you need a projection matrix to just align the two of the same size, and then you can feed it into an LLM. That's all they're doing. Do you see the sheer simplicity of the architecture? Lovely idea, right? Amazing. So sometimes, it's just the simplicity of the idea that gets you there, but it's very well done. And when this happened, this really took the world by storm. Lots of people started using it actively. So this was this paper, guys. Now I'm going to do another paper reading, but not after you have done some exercises. So here's the thing, guys, do it in groups, in your teams, etc. Don't leave it for later. Do it right now. The rest of the time, how much time do we have left? It's 2:30 till 5 o'clock. Give a couple of hours. And by the way, I'll also do Instruct GPT paper. I want to do that. So we have a lot of paper reading to do. As soon as you guys are done, let me know. But I want you to do this. Go to LLaVA GitHub. Now, this is it. LLaVA. So by the way, there has been a lot of development since then. The latest LLaVA is the LLaVA Next. Are we together? You can. LLaVA Next is 1.6, paper, etc., etc. I would suggest that if you have gotten the main idea, it's okay. But like one of you said, right, that I'm unimpressed with the response, you can try it with this. But the more important thing is to actually start using it at this moment. And this is what I want you to do. Install it, guys. Install it right now. Try it on some images. Right? Do it with Hugging Face, by the way. And try it out. Ask it to describe something. Ask it a question about your image and see how well it can answer it for you. Right? So please do this. Become experts at LLaVA, because the next step at some point you'll do is not just use it. I'll ask you to fine tune it to your specific use cases. I'll ask you, one of the projects you'll get is to take a problem where you can make it useful, but you'll have to fine tune it a little bit. So you'll have to create your own training data. Yeah. But that will come later. At this moment, become experts at LLaVA. I'll give you an idea what we are going to do next. We are going to do LLaVA 3D, and then we are going to talk about Instruct fine-tuning at the second half, at the final day. So we have 2 more research papers to read. As soon as each one of you can demo, but I want a demo that you guys are using LLaVA, please demo it. Yeah. If you go to Hugging Face LLaVA, they have a very good representation example here. This is the paper, etc. Where's the demo? They have a demo. So as you can imagine, LLaVA has gone through LLaVA Next, LLaVA Video, right? Video understanding, LLaVA 1 Vision. So LLaVA, there's LLaVA Med, which is used a lot, getting a lot of attention actually. So LLaVA has become a whole series of derivative work. I'll just cover one of them, LLaVA 3D, right? But I want you to at least start with the basic, play around with it. And I wish there was a demo here. There was somewhere a demo. Oh no, I had created the demo last time. Okay, so that's your thing for the next 2 hours, guys. But if you finish it before 2 hours, all the better. Let us regroup and